Hi again and welcome to section 3 of this course. In this part, we explore how the Firefly algorithm can be applied to a simulated space-time wrapping scenario. We investigate why such topic matters and why Firefly algorithm is a proper tool to solve this problem. What parameters we use and what would be our objective function here. You will learn how concepts like bending, curvature, and wrap fields relate to optimization problem, and how fireflies use these rules to find energy-efficient paths. By the end of this section, you will understand not only the math, but also how to connect physics-inspired thinking with a powerful bio-inspired algorithm. So let's begin. Section 3 is dedicated to solve a space-time wrapping problem by Firefly Algorithm. There are some basic definitions which we have to know before we start. What is a space-time? The four-dimensional fabric combining space and time where motion or energy can bend its geometry. Now, what is a space in real world and what is a space in the course? Space in the real world is the three-dimensional physical area where objects exist and move. A space in the course is the 2D coordinate system x and y where fireflies search for the best position. Time in the real world is the continuous flow of events from past to future, measuring change and motion. In the course, the iteration sequence showing how solutions evolve step by step during optimization. By the four dimensions we mean x, y, and z from space and t from time. By fabric we mean the real-world woven structure of a space and time becomes the coded grid of position and iterations forming the optimization landscape. Now, wrapping means artificial distortion or bending of a space-time that shortens distance or time between 2 points. Here we can see descriptions before in the visual form. We can see space, time, what we mean by fabric, what we mean by wrapping, bending, and 4 dimensions. Now there are some intermediate to advanced definitions here. Geodesic is the shortest possible path between 2 points in curved spacetime in physics. Bending effort or lambda is resistance against curvature, represents the energy needed to change a path's geometry. Wrap field is a simulated distortion field that alters how distance and time are measured. Objective function is a mathematical rule measuring how costly or good a candidate solution is, which we explained later. Firefly algorithm is a metaheuristic inspired by fireflies' light attraction, brighter, which brighter ones attract others, which is explained in the section 1. Attractiveness or beta is an important parameter of Firefly algorithm, is the strength of movement toward a better, brighter solution, decays with distance. Absorption coefficient or gamma is another parameter of this algorithm, which controls how fast attractiveness decreases as distance grows. Randomness or alpha is exploratory noise allowing escape from local minima. Intensity, brightness, equivalent of a solution quality, which is the fitness. Global best is the best position with the lowest total cost found so far. Distance metric, Euclidean norm used to measure how far two solutions are. Now, the most important part here is the objective function, our goal. So our goal or objective function is to find the optimal point, path endpoint, that minimizes total energy, the combined cost of distance, bending, traversal, effort, and wrap field energy. So we do the process to bend space-time efficiently, finding a point or a path where the energy cost to travel through wrapped space is minimal. In a simple term, finding the smoothest, most energy efficient least curved path from a start point to the target in a wrapped spacetime. So why does it topic matters? Space-time wrapping is important because it enables theoretical concepts like faster-than-light travel, gravitational navigation, and discovery of minimum energy path in an extreme physics environment. By simulating it computationally, we gain insight into how curvature, energy, and distance interact, which is valuable for optimization, robotics, astrophysics, and even AI path planning. Now, why we are using Firefly Algorithm here to solve this problem? Firefly Algorithm excels in solving this problem because it naturally balances exploration and exploitation, helping escape local minima in complex wrapped landscapes. Its distant space attraction makes it ideal for space-time scenarios which curvature and energy field influence pathfinding not linearly. Now we are going to formulate the problem and its solution. So we have some inputs. Each firefly represents a candidate solution, which is a possible location or path endpoint. Actually, the answer, which we are showing it with x. Also, d is the number of dimension. Here is 2, which is x and y. Number of fireflies is n, which is a number of possible spacetime path bending explored in parallel. Also, all the fireflies are in the bound of -5 to 15. Also, we have some constants, which is alpha, randomness factor. Alpha is quantum or thermal noise, help exploration beyond local curvature wells. Beta is base attractiveness, which physical interpretation for it is intrinsic gravitational strength, which shows how strongly bright fireflies attract others. Then we have light absorption coefficient, as I mentioned before, which is the curvature decay, how fast attraction weaken with distance. Then we have bending penalty factor, the stiffness of a spacetime, how resistant it is to bending, which is rigidity of a spacetime fabric, how resistant the curvature is. And we have wrap field, which is a static modifier simulating spacetime distortion. Higher values means a stronger curvature. Physical interpretation for it is artificial distortion of the metric, simulating wrap-drive curvature. So this is our objective function equation, which is the most important part. We have some mathematical rule and some physical conceptual meaning. So the first part of the equation shows measure distance distorted by wrap, which means geodesic distance through wrapped space, how long it takes light or an object to reach the goal. The second part is a quadratic penalty deviation, which is curvature resistant, bending spacetime costs energy. The last part is constant energy term, which is wrap field maintenance energy. Keeping the wrap active consumes power. So this function measures total energy required for a path or a location in curved spacetime. Lower the better. Lower this function value is means the smoother curvature, shorter distance, lower energy, exactly what physics wants for efficiency. Here in the Firefly algorithm, energy becomes light, which we show it with I. Low energy or lower objective function value is equal with bright firefly, which is the efficient point, and higher energy means dim firefly, inefficient or costly point. So brightness literally encoded energy efficiency in a wrapped time space. So firefly attraction here is the gravitational light pull, which actually it is between any two fireflies, I and J, which we show it with Ri and J. The closer they are, the stronger the attraction, like gravitational pull or curvature influence in general relativity. Bright fireflies, low energy, pull dim ones toward them, mimicking matter bending spacetime so other moves along that curvature. Also movement in the Firefly algorithm, evolution of a spacetime path in the spacetime wrapping, which shows by the following equation. This equation means Firefly I moves toward brighter ones, lower energy zones, physically like matter following curvature toward an energy minimum. The random term alpha adds in a small quantum-like fluctuation, creating exploration of the wrap field. After each move, positions are clipped to remain within defined boundaries, which is our cosmic box. Also, iteration in the FA algorithm is equivalent with time in the simulation in a space-time wrapping problem. Each iteration corresponds to time evolution, a discrete trick of cosmic time. The swarm keeps moving and space-time gradually stabilizes as the energy landscape smooths out. And convergence here means finding the stable wrap. After many iterations, we have the F-best, which is the minimization of our objective function. The swarm settles near the lowest energy point, which corresponds to the most efficient configuration of curvature and distance, which is the optimal wrap path from the start to the end throughout spacetime. The final objective value, last iteration fitness, is the minimum energy providing the algorithm found the smoothest, least resistance spacetime configuration. It is the most efficient way to traverse the curved universe. So this value in our problem, when we are solving it in a coding environment, corresponds to a 2D space like, for example, 1.6 in x and 1.01 for the y in our problem, which is actually global best position, the position value from the last iteration. Here in these figures, in the left, we can see blue dots, which are fireflies, moving toward the best firefly with the brightest light, which is shown with the red cross, which is our global best, or the best position. Also at the right, we can see convergence of the algorithm for the space-time wrapping problem. As we can see, convergence happened in the iteration 10 and stabilized. Now we go and take a look at the code in the Python environment to simulate all the results we can see in this slide. Okay, now we are in the Python environment under Anaconda. Here we can see the main body of the Firefly algorithm here. Population size, we just considered 50 fireflies in 100 generations. For more information about the Firefly algorithm, please refer to the section 1. Also, for testing this algorithm, we choose exactly the 8 functions which we choose for the algorithm in the section 2, which are sphere, Matthias, Rosenberg, Pavel, Rasrigin, Ackley, Eggholder, and Bale from 4 different categories. So when I push the run button, we can see in the right the performance for each function. So we have 2 plots. We chose Firefly algorithm on function landscapes with best solutions. Here we can see a sphere, which found the global best. Also same for the Matthias, for the Rosenberg, for the Bale, for the Eggholder, for Ackley, and for Rasrigin. Now for Rasrigin, it could be any of these 9 spots. But Pavel is 4-dimensional, so it's not possible to plot it. Also, we can see the convergence for each function using Firefly algorithm. For space-time wrapping by Firefly algorithm, we have this code. Here we just imported the required libraries. This line helps to produce new random solutions each time. So basically, if I decomment this, it's gonna produce the same solutions, but we don't want that. We want each time random solutions. So we are going to comment it. Also here we can see the objective function, which is distance to target with the wrap influence. Also the bending effort, the traversal cost, and wrap field maintenance energy. At the end, we are going to combine all together and we have total cost. The parameters for the Firefly algorithm is 100 fireflies in 2 dimensions of x and y in 50 iterations. Also, we have alpha, beta, and gamma values as follow here. Also, we can see the bound of firefly movement here from -5 to 15. This is the Firefly main loop right here. At the end, we are going to print the best Firefly index, also the position of the best Firefly in x and y axes, and also the minimum total energy of that Firefly to find the best path. So basically, this line shows the minimum total energy required to find the best path. Also, we have plots here for iteration. We have the visualization of the fireflies and also the animation of fireflies moving toward the best target. Here we can see that fireflies moving toward the global best. And this is the convergence of the Firefly algorithm for the spacetime problem. As we can see, the convergence happened right after the 10 iteration.